Okay, with your highlighter, I need you guys to highlight. Let me make it all nice and broad. Right here, inverse sine. Inverse sine. Those are the answers. Inverse sine. Those are the answers. Negative pi over 2 to pi over 2 to get that one principal value is what we called it, that your calculator would spit out. That one principal value. For instance, over here, if you were to give me 11 pi over 6, I would take off points. But it's the same location. But it's not in between there to there. If you were to give me 11 pi over 6, you're not wrong. Now, if you were to give me 7 pi over 6, actually you're wrong. It's not even the right location. So you need to know I'm only looking between negative pi over 2 to pi over 2 for arc sine, but that's not the only inverse trig. What other inverse trig do we have? How about arc cosine and arc tangent? For inverse cosine or arc cosine, we need to circle these ones. Only 0 to pi, only first, second quadrant. That's the only place we're looking. First quadrant, positive cosine. Second quadrant, negative cosine values. For inverse tangent, only here. Negative pi over 2 to pi over 2. Very similar to sine. Negative 90 to 90. Fourth quadrant and first quadrant. If tangent is positive, first quadrant. If tangent is negative, second quadrant. Inverse tangent. Now, no. Is today going to be inverse cotangent and inverse cosecant and inverse secant? No. No, not really. We'll look at those and how to solve those. We don't necessarily, at least right now, at this level, we don't need to go looking at the graphs and memorizing the graphs or even looking at these ranges because it might not be what you think, which is why we need to look at it. But they are built on sine, cosine, tangent, inverse, similar to how cosecant, secant, cotangent are built on normal sine, normal cosine, normal tangent. They're built on them differently. They're related differently, but the same way we use those buttons in our calculator to find the one, we're going to use the inverse buttons in our calculator to find the other. It's just a little tweaky, a little weird as to how it happens. So we'll talk about that in just a second. But did you guys highlight what I told you to? You sure? Okay. Then let's move ahead to applications. This is what we didn't get to. And some of you guys, when you were doing homework, this is where you could have stopped. Some of you guys, when you were doing homework, this is where you could have stopped. Maybe should have stopped if you weren't willing to do a little extra work and look at the examples in the book. So let's figure out what's going on when you start seeing normal trig with inverse trig. Let's start seeing what happens when we start seeing normal trig with inverse trig, and somehow we have to simplify. Now, I've given you tricky examples. So let me give you a second. Get down the page. I've given you tricky examples, so I need you guys totally focused when we do it. So let me give you a minute or so to set this up. If you don't mind, I don't think I need your full attention to label a triangle, so I'm just going to label the triangle as you guys are getting set up, if that's okay. As you guys are still writing notes, just give me a favorite trig function. What's a favorite trig function? Pick one. Cosine? Okay. Since I had all three sides, I could choose anybody. So that's why I was asking. So cosine equals we can take cosine inverse of a cosine to undo. So far, when you were solving right triangle problems in section 4 was it 6 where we were solving those triangle problems? Oh, sorry. 4.4. Yeah, it was before the unit circle quizzes. When we were solving right triangle problems, there was like the Washington Monument problem, and I think there was That was in the notes. In homework, I forget what the word problem was. You guys didn't need help on it, whatever it was. The right triangle problems, we were given angles and solving for like missing sides. But what if we're given the sides and we were missing the angle? You can get inside by taking cosine inverse. And that makes sense, right? Don't inverse operations usually undo? Addition undoes subtraction, square roots undo squares, undo to the power of. Good. What would undo 10 to the power of? Log, common log. Okay, so we're used to inverses undoing. So the cool thing is cosine inverse can undo a cosine. Like not just divide by cosine, but undo the actual cosine happening to the x, which is pretty cool because then we can actually get to unknown angles and solve for them using that spiffy cosine inverse button. But what we need to realize is, once again, when we look at an inverse, the answer coming out is an angle, which is why we went through and highlighted all those ranges, all those answers coming out of inverse trig. What's coming out are angles, and what's going in are ratios. And specifically, if this is a cosine inverse, isn't this an adjacent over a hypotenuse if we were to actually label it, right? So ratios go in, angles come out. Just think of a cosine inverse or any inverse trig as a little factory where the ratios go in and the angles spit out. The ratio that goes in has to match the trig function or else it's going to mess up the machine. It's not going to work. So whatever's going in for a cosine inverse, I need adjacent and hypotenuse. So the cool thing is that inverse trig cancels out normal trig, but then we have issues like this. Because let me show you the answer to this real quick. If you were to do this in your calculator, even going to degrees, so it wouldn't be all nasty and decimally, if you tried to plug in second sine of 5 pi over 3 decimal, it would not be 5 pi over 3. It would be negative pi over 3. What changed? What changed? We can just cross out, right? Just the answer 5 pi over 3. No. You could do it in your calculator. It's not going to be, the decimal is not going to work for 5 pi over 3. It's going to be negative pi over 3. If you were to do it in degrees, this is the exact same thing as arc sine, or sine inverse, of sine of, what would that be, 300 degrees? The answer wouldn't be 300 degrees. The answer would be negative, nope, negative 60 degrees. But why? What happened when I threw that angle into the trig machine and then it got spit into the inverse trig machine and it came out different? What happened? The range. Didn't you guys just highlight what's allowed to come out of arc sine? What's allowed to come out? You can go look. What's allowed to come out? All that's allowed to come out is negative pi over 2 to pi over 2. Question, is 5 pi over 3 fit in those two angles? 5 pi over 3 goes all the way around. I'm supposed to stop and stop. So what's another way of going all the way around? Going negative. So there are still those restrictions to inverse trig where something might change when it gets thrown in. Something might get changed when it gets thrown in. So technically, if we were to do this step by step, like with PEMDAS, arc sine of 5 pi over 3, sine of 5 pi over 3 is negative root 3 over 2. And in this interval, which angle will have a ratio of negative root 3 over 2? Not the first quadrant, fourth quadrant, but going negatively pi over 3. So maybe some of you are already wary of letter B and you're like, I don't think the answer is pi. And you're totally right. It's not pi, even though you're like, cross, cross, ha-ha. Nope. But why isn't it pi? This is also restricted. This is only allowed to spit out 0 to pi. Wait, it's only allowed to spit out 0 to pi. We didn't highlight this, but what's the only types of numbers allowed to go in? Negative 1 to 1. Why is this answer DNE? Cosine inverse of pi. Cosine inverse of 3.1415926, a ratio of 3.1415926, can an adjacent over a hypotenuse ever equal 3 point anything? Can this side be 3 times longer than the hypotenuse side? Because if A was 3 times longer than C, is that a right triangle anymore, guys? That's not a right triangle. It's impossible. I can't have my adjacent over my hypotenuse be anything larger than 1. If you guys were to plug this in your calculator, that would be DNE. But I also need you to realize if you didn't have your calculator, it would also not exist. So what are the 2 examples below showing you? It's great. The inverse trig can be used to undo normal trig in algebraic expressions and equations. Great. But when you're given examples with specific angles and specific numbers, you have to keep your wits about you. And you have to have in your mind what's legal. What's legal to go in as a ratio? Only -1 to 1. What's legal to come out as an angle? Well, for cosine inverse, only 0 to pi. So if something's different, you have to change it. Does that make sense? Okay. And what if you're getting nasty decimals in your calculator and you're like, I don't know the decimal equivalents of radians? Change to degrees and then just get an idea of what's going on. Is that okay? Okay. Now that's kind of introducing one type of application of these. That's just kind of introducing one type of application of these. Now that you guys think you have it, I've moved the page so you can't see anything that we've done before, even though it might be in your notes. I want you to do one last example. What is this? Example 3? Example C? Do one more. Show me that you really know what's going on. Example C. Before we totally move away from this whole regular trig with inverse trig with regular trig. Show me you know what's going on. Check in your groups, do they agree? Everybody's here? Adam. Because it can be answered just before pi over 3. No. Because what is sine inverse allowed to have? So which angle between positive to -90 can match up? 4 pi is over here. I'm supposed to answer over here? Which one? The answer isn't an angle that has to be the same location. The point isn't the location. The point's not the coterminal. The point's not the location. The point's not the coterminal. The point is the value. What value does sine have here? Right? Can sine be negative here? Forget that. What other angle would have that exact same? The point is not the placement. The point is the value. Anybody get negative pi over 3? Pause. Go to your calculator. See if I'm right. See if I'm right. What's second sine of 4 pi over 3? Go. What's second sine of 4 pi over 3? I'm going to plug in 4 pi over 3. It should cross out, right? It should be the exact same thing. Except there are restrictions. 4 pi over 3. Are you guys getting the decimal? 4.188790205. When you do second sine of 4 pi over 3? No, you're not. You're not getting 4.188790205 when you plug in sine inverse of sine of 4 pi over 3. I know, because I have it. What are you getting?
Well, that's in radians.
You're supposed to be in radians.
Radians is negative 1.
Yeah, your answer is negative 1.04719. It's not 4.188. This guy is, this little guy right here, is 4.188790205. But when you solve, you end up with negative 1.047197. Those don't match. You can't just cross out. What happened? Who is this guy? Did you plug in negative pi over 3 to see if we were right? Negative pi over 3, 1.0471975551. What happened? Sine inverse only spits out certain answers. Am I looking for coterminal? No. What am I looking for? Value matching. Does that make sense? And well, with PEMDAS, if we were to actually solve this, we would have done the inside the parentheses first. So it would have been sine inverse of negative root 3 over 2. We're not answering based on this guy. We did sine of that guy, but we're answering based on his value. And his value gets us here. Okay. Kim.
Why is that negative 2 pi over 3?
Because that's illegal too, kiddo. I'm only allowed to go to negative half pi. Not to negative 2/3 pi. Yeah. Okay, last application. I think this is where homework ended. A couple girls in here yesterday, I saw two of them doing it. What happens if they don't give us a number? Can we give them a number in return? But for these ones, if there's an x in it, we're not trying to give them a number in return. It's not a definite ratio. It's more of an idea of a ratio. Why am I calling this guy a ratio? Who's he going into? Sine inverse, right? Think of it this way. You're going up to, what are we going up to? What do you guys buy that requires this anymore? Does anybody even use vending machines anymore?
Yeah.
You do? Okay. What if you go up to a vending machine and try to use one of those dollar coins? Do those work very well? They do work? No. Bummer. What if you go up to a vending machine and try to use a $2 bill? Those ones are rare. Will those work? Not usually. Usually it says something like 1, 5, 10, 20, right? Usually it says like these bills but not other bills. If you went up with can't use the $1 coin. A $2 bill and try to use that. Or maybe you go on with some Leon bucks and try to use those. Is that going to get you any candy or any soda? Or any, I don't know, healthy water, whatever else they sell in the vending machine? No. Leon bucks aren't going to work. Why not? Do they work in Mrs. Leon's classroom? Yes. Do they work in vending machines? No. Why? Because it's the wrong currency. What's the only thing that can go inside inverse trig? Ratios. What's the only thing that can go in normal trig? Angles. You have to think of what your currency is. Okay? So, ratios go into inverse trig. Specifically, what kind of inverse trig is this? Sine. So whatever you put in, it's going to say like, oh, you mean opposite over hypotenuse? That's exactly what they meant. Now, if this was an arc cosine, what would these be? Adjacent over hypotenuse. If it is arctangent, what would these be? Opposite over adjacent. So SOHCAHTOA. So whatever goes in, you have to look and say, wait, what am I putting this into? Oh, a sine inverse. So number 1, ratio, that's the currency. And number 2, we have a hypotenuse. So guess what we can do with a arbitrary right triangle. For any theta, we can say, oh, hey, according to you, fine. Opposite, that's your hypotenuse. Hypotenuse. But what are they asking for? So technically, we could say, hey, remember how arc-trig goes back to a theta? All right, Gavin, quiet the pennies. No, thank you. Currency, it sparked the illustration. Arc-trig gets us to angles have triangles. What are they asking for that angle, for this triangle? I need an adjacent hypotenuse. And here's the cool thing. I already know my hypotenuse. That's easy. It's the same as that. But what's the problem? I don't know. There is no number. They didn't tell me the number of that guy. Okay, fine. What's the formula? Oh. Hey, guys, don't we have something called Pythagorean theorem? And doesn't Pythagorean theorem say I can solve for an unknown if you just give me the other guys? Now, some of you might be like, but we don't know the other guys. But wait, there was an x to begin with. There can be x at the end. So how do I solve for a? Don't I subtract x squared, and don't I square root both sides? A is going to equal 4 minus x squared. So guess what's going to get plugged in down here? If you wanted to be super jazzy, I suppose you could say plus or minus, being like, I don't know, you didn't give me a quadrant. I guess technically you could say plus or minus. To be honest, technically you should put plus or minus, because cosine can be plus or minus depending on the quadrant. And if they don't tell you the quadrant, you can't say which one it is. I think the back of the book doesn't put a plus or minus, but you technically should. That's the final answer. Unless they give you for x and you plug in, but otherwise, nope, that's it. So for whatever x over 2, because of Pythagorean theorem, because of arc-trig giving me ratios, because of all this coming back to a right triangle, I can say the cosine for whatever x over 2, not even just unit circle, will always end up being this. Okay. So was there a problem there was an x at the end? No. Why? There was an x to begin with. If they didn't give me a number, I can't give them a number answer. But if they give me an x, well, I can give them an answer based on x. What did I do? Saw the ratio, used the ratio, finished the triangle, and then gave them what they wanted. Saw the ratio, used the ratio, finished the triangle, and gave them what they wanted. So you guys, ready, set, go. Ooh, you have to remember who secant is. Sokoto wachoshiko. Go. You're welcome. Sokoto wachoshiko. Not sure that will help. Oh, baby guy. Okay, check in your groups. Some groups are still stuck. Take a little more time, but check in your groups. Turn to me and give me a thumbs up. I was going to say a high five. Oh, no. Oh, no. Hold on. Why did I say cho? Why did I say cho shakal? Sha? Cho sha. Sha. Who is 2x over 3? Hypotenuse over adjacent. So let me remind you and your group really quickly of the procedure. See the ratio. Okay? See the ratio. Finish the triangle. Wait, did you make a triangle yet? Did you label the sha? Hypotenuse and adjacent? See the ratio. Finish the triangle using what theorem? Pythagorean theorem. See the ratio, finish the triangle, give them what they want. Toa. Okay, one more minute. See the ratio, finish the triangle, give them what they want. Toa. It's going to have x's. Okay, now give me a thumbs up if you're ready. Oh, that's it? Hold on, check in with your group, check in with your group. Some of you guys are like, I'm ready, but your group is sad. Some of you groups that are sad, turn to the ones who just gave thumbs up next to you and see if they can help. Any other groups need to reach out? Reach out. I see one group reaching out. That's good. All right. Now I get to play. I know, I've been trying so hard. See the ratio.
Be the ratio. Adjust the ratio. Do the ratio.
Something like that. Maybe not quite. Finish. Well, I guess you have to start and finish, huh? Finish the triangle. Give them what they want. If you want, you could do plus or minus because they did. Ooh, they did give you a quadrant. They did give you a quadrant. Tricky, tricky, tricky. So we have to come over and see what quadrant do they want this in. They technically want this somewhere in the fourth quadrant. Uh-oh. Tangent of any theta in the fourth quadrant is negative, right? Can't put plus or minus on that one. Dun, 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 dun. Wait, wait, we were smart. This is 2x minus 3. Kill the puppy. No. Isn't this 2x plus 3 times 2x minus 3? Is that a perfect square? Can you square root this guy? Can you distribute a square root like a multiply? Puppies dying everywhere. Questions? Did you see the ratio? Did you finish the triangle? How? Ooh. C squared minus B squared is A squared, so A is the square root of C squared minus B squared. Or whatever. B equals the square root of C squared minus A squared, whatever you did. Finish the triangle, then did you give them what they want? Ooh, and check the sign? Okay, one extra step. Check the sign. Don't worry, it's 1 page for 3 inverses. That's not too bad, huh? 1 page for 3 inverses. How do you think about inverse cosecant, or inverse secant, or inverse cotangent? Now, first of all, cosecant equals 1 over sine. Cosecant, normal cosecant. Secant equals 1 over cosine. Cotangent equals 1 over tangent. Got him, coach. Right? Cosecant equals 1 over sine. Secant equals 1 over cosine. Cotangent equals 1 over tangent. What does that mean? The ratios of the reciprocals are reciprocals. What? They're called the reciprocal functions because their ratios are reciprocals. Meaning, if I was trying to answer what is secant of, what's an easy one, of pi over 3, that is 1 over cosine of pi over 3, which means secant's ratio is equal to 1 over cosine's ratio, which means I take cosine's ratio and I flip it. Secant's the reciprocal of cosine's ratio. That's why it's called the reciprocal function. Reciprocal functions have reciprocal values, aka ratios, not angles, and this is where it gets tricky. Because when you come down here to do arc cotangent, it does not equal 1 over tangent inverse because this is all of a sudden an angle, not a ratio. Ratio, I can't do 1 over. So instead, I actually need to go find the ratio, which is right here. I actually need to go find the ratio. Fire's back. I need to go find the ratio and say, wait a minute. Cotangent's ratio gets flipped from tangent. So here's what you get to do. We are going to use tangent inverse. But tangent inverse can't take cotangent's ratio. And 1 over tangent inverse won't get me what I need. Tangent inverse needs the reciprocal ratio. Tangent inverse needs the reciprocal ratio. So that's what builds up to how do you find cosecant inverse? You do sine inverse of the reciprocal. How do you find secant inverse? You do cosine inverse of the reciprocal. And how do you find cotangent inverse? We use tangent inverse of the reciprocal. If I were you, because this gets real tricky in the sense of your brain is going to really want to just do 1 divided by sine inverse and 1 divided by cosine inverse and 1 divided by tangent inverse. But whenever you do that, you're saying, oh, yay, flip the angles. No, 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 no. Got to flip the ratios, and that's how we flip the ratios. So highlight those little baby formulas so when you are allowed to use your calculator, you're not going to have a second cotangent button or a second cosecant button or a second secant button. You're going to have to use the second reciprocal button of the reciprocal ratio. You're going to have to remember those little baby formulas or at least how to use them. Plug and chug to your calculator. It could be a degree. It could be a radian. Just make sure if it's a degree, you label it with a degree mark. If it's a radian, you don't. We had actually one like this a little bit ago. So I'm going to go ahead and instead of doing a homework help, hold on, it's one homework. What's it homework number 29, right? Do you guys agree with that from what you did? Okay. There used to be parts 1 and 2. Now there's not. It's just one homework in Google Classroom. I'm going to show you guys what section you're going to be doing over break. Over break! Go look at homework. So your homework is to finish up this section. Whatever you didn't do last night, some of your classmates have the whole thing done because they were like, I can figure this out with some book examples. The rest of you guys got it now. You're finishing up homework number 29, posting it in Google Classroom. However, there's going to appear by the end of the day a new Google Classroom assignment for homework number 30 due Monday. Oh, no, we haven't done it, which is why attached in the assignment is going to be videos from last year of me doing it. What are you going to do? Take notes and do the homework. Come Monday ready to go over questions on 4.7 and 4.8 homeworks. Why? Because we're a little behind. We were supposed to have a chapter 4 test today. So instead, you're doing one section over break with me on a video from a year before. You can put me on 1.5 speed and skip over the blah, blah, blah at the beginning or the end of class. Totally fine. You're going to attempt the homework, but look at what the homework is. Take all the stuff you just did and apply it to problems. So the notes are basically examples of some word problems with triangles from all of chapter 4. Then we're going to come back, go over homework questions, have a review, and take a test real fast. So, should you totally ignore honors pre-cal over break? But do you have a whole weekend a little bit just to kind of finish up chapter 4, not have had to have stressed about a test this week and come back and say, all right, I'm all ready and I'm all caught up. Let's do this thing. Hopefully. Your test for chapter 4 will have 2 parts, a calculator part and a non-calculator part. A calculator part and a non-calculator part. So those of you that are like, I don't need to know my unit circle anymore. Yeah, you do. But those of you that are like, I don't ever use my calculator. Okay, so make sure you know how to use your calculator when you're doing 4.8, but also make sure you don't forget the unit circle at the same time. Are we good? Keep an eye on Google Classroom. If you have any questions, pop me an email or comment if it's something the whole class might want to know on the assignment. Sound good? Get out of here, cool kids. It's Chapel, Mr. Carmichael. Yes. Best day ever. Bye, guys.